She's a graduate student from LPL, and she'll be talking about comets and the Rosetta missions. Take it away.
Hi guys, yes, I will be talking about comets, because comets are cool and they're really the best thing ever. Maybe not, but they are. So I'll be saying a few things about them and hopefully you'll enjoy it and follow along. So first, I want to talk about comets through time. Comets have been known for quite a while, and for example, the first ones who took good records of them were the Chinese astronomers. This is a silk painting of comets dating records through over 15,000 or 1,500 years. And so as you can see here, this one was specifically made in 300 BC. You can see several comets. You can see their tail shape, or at least what people thought their tail shape was, as best drawn by hand. And then you can also, underneath is written the disaster that it was associated with. Next, we have other reason why comets are important. They were always thought to be bad omens. So people just saw a comet, were like, something bad's gonna happen today. Something bad did happen, as it always does, and people were like, hey, it's because of the comet. Which is kind of ridiculous, but it's true. So here on the, I know my rights and left, on the left-hand side, we have drawings of comets. People thought they looked like swords. That's why they must bring about fights. And you can see different tail shapes as well. And then on the right-hand side, we actually have a drawing of Germany with 3 different comets that came in 1680, 1682, and 1683. And in the front, I don't know if you can see it very well, you can see the 3 horsemen. And so the comets in this case were associated with the apocalypse. And we also went back through time, saw this, and we're like, okay, the 1682 comet happens to be Comet Halley. But I'll talk more about Halley in a while. So here we come to our first trivia question. So what disaster has not been blamed on comets? Is it the assassination of Julius Caesar, the eruption of the Vesuvius in 79 AD, the Black Death coming to England, or Francisco Pizarro's arrival to South America to brutally conquer the Incas?
So raise your hand if you think you know the answer.
Raise your hand if you think you know the answer. I see. Sorry.
Go ahead.
Anyone? It's a multiple choice. It is not A.
Right here.
It is not the plague. The plague was also blamed on comets.
Right here.
It is not D.
Oh, B.
Anyone want to shout out B to get the prize? B. Raise your hand. Seriously. It is B. The eruption of Vesuvius is not blamed on comets, surprisingly. That probably just means there was no comet around when it erupted, and so no one had anything to blame it on. Okay, now I'm going to talk a little bit about my favorite comet ever. And why is it my favorite comet ever? No, it's not because it's truly evil. It's just because I studied it for 2 years and know way too much about it. But anyways, Comet Halley was thought to be really, really evil. For example, it was blamed for earthquakes, for illnesses, for red rain, and for the birth of 2-headed animals. Of course, like that's what comets do. They make 2-headed animals. It also was blamed for bringing the Black Death to England, as we just talked about. It predicted the invasion of William the Conqueror into England, as you can see on this tapestry up here. So this is a super long tapestry, and one of the scenes has Comet Halley in it, foreshadowing the bringing of William the Conqueror. And so for the English who lost, it sucked for them. But of course for like William the Conqueror, it was a good omen because he won. And then because Comet Halley is so evil, it was excommunicated by the Pope in 1456. Why not? You can excommunicate everyone and everything, including the poor comet. So, a little bit about the good parts about Comet Halley and how it's not really evil. So first, Edmund Halley, which is the guy pictured up here, is a super cool dude. I like him. In 1705, he wrote the synopsis of the Astronomy of Comets. So he gathered all the knowledge we knew about comets and tried to get some science out of it. So really, he's an astronomer and a scientist. He, from his data that he collected, saw that there was one specific comet that came back every 76 years. That happened to be Comet Halley, as we name it now. Back then it had no name, no one knew it was the same comet. He predicted that this comet would come back in 1758, and it did. But he had already died in 1742, so he didn't see the predicted comet. This was the first comet that was predicted to repeat, and that showed that comets weren't erratic and weird and unpredictable, as everyone thought. And so because the comet came back the year he predicted, people were like, let's name it Halley's Comet, because he had said it would be here. And since then, we followed Halley's Comet through time, and we have seen it over and over again. For example, the picture we have here below Halley is a 1910 photographic plate image. So if you don't know what a photographic plate is, it's this giant thing you're putting under a telescope, and you're observing the comet for a very, very long time to gather enough light, and then we develop it afterwards. They're really, really a pain. You don't want to deal with that anymore. Nowadays, we're lucky enough to have digital cameras to see the picture of the comets and get better data. So remember how I told you I studied Halley's Comet for 2 years? I did. That was a few years ago, but I looked at the 1986 apparition, which means when the comet comes closest to us. And that apparition, we still have some images on photographic plates. So I know how much of a pain they are because I had to deal with them. But luckily, most of my data was digitalized. And then the next time it returns, so you should all mark your calendars, mine is already marked, will return in 2061. It's a little while from now, but it'll be super bright. So it's supposed to be a magnitude of minus 0.3. So if you think about magnitudes, Sirius, which is the brightest star in our sky, is a magnitude of negative 1.4. The more negative you get, the brighter it is. Vega, which is another pretty bright star in our sky, is a magnitude of 0. So Halley will be somewhere in between those, which means it will totally be a naked eye object. It's also really well positioned. So 2061, mark your calendars. Here's our next trivia question. Which writer said, I came with Halley's Comet in 1835, then it is coming again next year and I expect to go out with it. Then the writer actually died the day after perihelion. Yes, I see people.
Okay, right here. We have a framed poster of Halley's Comet.
Framed poster of Halley's Comet. Can I get that? I know the answer. Okay.
Is it D?
It is D. It is Mark Twain. The other people, I gave you their birthday or birth year and death year, so you knew I wasn't lying. But here it is. Okay. So now we've talked about how comets are evil. We've talked about how they really didn't cause those disasters. But wait, there's a comet that actually could be the cause of a disaster. Maybe. We're not actually quite sure yet, but it's our best hypothesis. On June 30th, 1908, there was an explosion over Siberia. The explosion caused all the trees to flatten out and cause a big crater. This is called the Tunguska Event. It was heard by a lot of people. However, no one was there because it's Siberia and it's always cold and no one really wants to be in Siberia. So a few people about a few thousand kilometers away heard it and reported it and marked it. Later, someone came to visit the place where this explosion had been, found it, and found a big crater that had, with the trees flattened up to 770 square miles. So, luckily, no casualty. Since there was barely any meteorites or meteoritic material found, so meteorites weren't found around it, a good explanation is that it's actually a comet that exploded, and then it would have melted away and you wouldn't have anything left because either it would be in the atmosphere or it would go away as liquid. So maybe comets do cause disasters. And that also brings the idea that we know those big spatial objects could hit us and kill all of us. So really they could bring bad luck one day, but not predicting that England will be conquered. Okay, so now I'm going to tell you a little bit about a comet. But first, one more trivia question. Where does the word comet come from? Is it from the Greek word come, meaning long-haired? From the Latin word comes comitus, meaning companion? From the Lingala word coma, meaning comma? Or from the Finnish word kami, meaning mistake? It's A? Yes, it is. It is from the Greek word coma, meaning long-haired. By the way, All of these are real words, and I looked really hard for anything that would kind of resemble a comet in the name from different languages. I had fun making this trivia question. But let's talk about what a comet is. So, a comet anatomy, it has to have a nucleus, a coma, a gas ion tail, and a dust tail. So the nucleus is the part in the center that's actually solid. So it's a solid ball of material. We can either call it a dirty snowball or an icy dirt ball, and that kind of depends on which side of the debate you are, and also there's kind of a distinction with age. The older people like to stick to the name they had back in the days, and then the newer people are like, actually, you're wrong. But I'm not going to talk about that too much. We don't actually really have a clear definition, because all nuclei are going to be different. As you can see here, they all have different shapes, they all have different sizes, they all have different composition. So really, you can't predict how the nucleus of a comet looks by just being like, oh, it's a comet, it must be spherical. No. But you have a few comets, like Temple 1, for example, that is very spherical compared to 67P, which the name is up there if you want to practice it, but I won't. And so 67P is the one that Rosetta went on, which is why we have such a beautiful image. While Hartley 2, we had a spacecraft, and then Halley, again, my favorite, so I had to include it. And so comets, the nuclei are very, very dark. So we think that it's about as dark as coal, which is hard to imagine from these images because they're really bright. That's because we kept our lens open for a long, long time to get all the photons that we could, and then we stretched it so that we could actually see it. But really, it's about as dark as coal. The best way to imagine what a comet nuclei looks like is imagine you don't live in Tucson. You live in a place where there's actually snow. Okay? In this place where you have snow on the parking lots, you have the plows that plow it away and stick it all in a corner. So it's kind of dirty. And then you let it melt for a while until you're left with still a little bit of ice, but mostly the gross stuff on top. That's what a comet looks like. Appetizing, right? Anyways, the next part we're going to talk about is the coma. So the coma is kind of the outer envelope of the comet. It's really close to the nucleus. So remember, I think I forgot to mention it, the nuclei of comet are about 10 miles long. The coma are much, much bigger, and they give the comets all their fuzzy appearances. So whenever you're looking at a picture of a comet that is not from a spacecraft, you only see the coma and the tails. You don't ever see the nucleus. It's way too small and buried in the coma. And so coma is, again, from the Greek word that means hair. It's usually dust, gas, and ices that surrounds the comet. And then it forms once the comet, so the nucleus of the comet, that is not sublimating, it has nothing yet. It's coming close to the sun, and then the ices on the comet melt away and sublimate, kind of like dry ice. If you've ever played with that, you know it sublimates and it doesn't go straight from solid, doesn't go through liquid, it goes straight from solid to ice, or to gas. And that's what happens on comets, because it has a very low pressure, so it can't form the liquid. And so the diameters of these coma can be about the size of Jupiter, but we did have one that was the size of the sun. And this is Comet 17P, which is called Holmes as well. Usually, other than Halley, who was the first one, most of the comets are named from the people that first discovered them, in case you're wondering where all the names come from. And if there's more than one name, that means there were 2 observers that night who were lucky enough to see it. And that's how we get our names. So comas are pretty big, they're fuzzy, they're full of ice, dust, and gas. And then we have 2 tails. We have the gas ion tail, which is the one that is formed from ion or plasma, which is when you have molecules that are ionized by the UV sunlight, so they break apart, they're ions, so they're charged particles, and then these molecules follow the solar winds. They're very coupled to the magnetic field of the sun, which is why they always point away from the sun. So this is the cool part. Tails don't point in the direction opposite from where they're going. So if you think of like an object going and you always see the tail on the other side, that's wrong. Tails of comets point opposite from the sun. So when a comet is coming towards the sun, yes, the tail will point away from the sun and from the direction it's coming from. But if you're going away from the sun, the tail will actually point in the same direction that the comet is going. I think that's cool. Because once you realize that, you're like, wait, what? What have all those cartoons ever told me about the tails of comets? Yeah, no. And so the ion tail is blue, and that's because one of the main molecules of the ion tail is CO+. which fluoresces in blue. So the fluorescence is when the ion gains some energy and then it releases it later, kind of like glow-in-the-dark stars. If you've ever had those on your ceiling, if you were a nerd like me. That's what they look like. And then finally we have the dust tail, which this one's mostly made of dust. And the dust particles are about the size of smoke. So if you were in the dust tail, it would look like you were near a campfire, other than the fact that it's much less dense and you wouldn't actually see them. The only reason we see these tails is because they're really, really big, and so they reflect a lot of light from our point of view. And the dust tail are usually yellowish, and that's because they directly reflect sunlight. And that's where they get their color. These are not as coupled with the solar wind. They're still a little coupled because the solar wind kind of drags them along, but they're not as coupled. So from there, you can kind of tell the direction the comet's going because it will be separated from the ion tail. Okay, and then one thing that I think is cool is that most of our meteor showers are associated with comets because the tails leave the dust behind, and when the Earth goes through it, we get the meteor showers. For example, the Orionids in October are from the tail of Comet Halley. It's still my favorite comet, that's why I know that. So, how do comets form? I think this is also pretty cool, and it's really why it's important to study comets. So, if you've ever heard a model of the formation of the solar system, we have first a giant cloud of dust and gas that condenses down. The little particles coalesce together, so they clump together, and they form these things we call planetesimals. So they're smaller bodies, not the size of planets, they're small planets. These eventually combine together to form the bigger planets, or don't combine together. And the leftover planetesimals are either the asteroids, such as in the asteroid belt, or the comets further out. And that's how we form comets at the beginning. So you can see in the image in the bottom, if you can see it from there, you kind of have a yellow part, that's where most of the gas nebula is, and then further out is the frost line, so that's where these gases condense out to form the ices. These ices are then what form the comets. Okay, so there are two ways that, well, there are many ways, but the two main ways that comets come close to the sun is either they're originally in the Kuiper belt, where they form, they're perturbed by Neptune or Jupiter, or maybe hit another Kuiper belt object, but that's surprisingly less likely, because there may be a whole bunch of them, like hundreds of thousands of them everywhere, of asteroids and comets, but they never hit each other, or very rarely, because space is giant. And so they fall down because, well, Jupiter or Neptune can trap them down, they fall down, or they can fall down from the Oort cloud, which is this giant theorized cloud, because we don't really know any Oort cloud objects, they're too far away. And these are usually perturbed by passing stars, which is really weird to think about, because you think, well, this thing is still in our solar system, right? And it is, kind of. But there are also other stars that affect the Oort cloud, and that can make the comets fall down. And so comets that fall down from the Oort cloud are usually dynamically U comets, which means it's the first time they've fallen down, and then once they leave, they'll probably leave our solar system forever, or at least for as long as anyone will ever remember that they came. So that is because they're on unbound orbits, or so we think. And then objects that come from the Kuiper belt are usually more stable. These are called short-period comets at some point, and so they repeat their orbit eventually, and that is how we know, for example, that Comet Halley is coming every 76 years, and it's been doing that for a long time. Okay, so why are comets important? Why have I been talking about them for the past 18 minutes? It's because, well, first they have hydrocarbons, which are the building blocks of life, eventually. The thing is that with life, I don't know if you knew this, and I think it's a really weird fact. We know what we need to make life. We know once we have the first inch of life, how to get all the way out to what we have, or at least we have a pretty good idea. We don't know how to go from the blocks to something living. And so people have said, well, why couldn't life come on comets from other sources? I think that's weird. I don't actually know. I'm not going to pretend I know how life forms. That could be a thing. Another thing is that comets could have brought some of the water to Earth. Well, we know it brought some, because, for example, the one in Russia that fell, it probably had water, so yeah, it brought some water. Not enough to, explain why we have so much water. But we think that it may have, some comets have the same composition as the water on Earth. By that I mean it has the same isotope of hydrogen to deuterium, which is a heavier hydrogen. So we think that some comets could have caused that. Not all of them, because now we have like comets that match Earth's water exactly, and then some that are so far away, it's like you could not have brought it in here. So that's one thing. But the thing I'm the most excited about, and the thing that I really want to help answer, is how it explains the formation of the solar system. So we know how the solar system formed-ish. We're not quite sure. It's still all a big blur. We tell people we know, but really no one knows. And so learning about comets can help identify things like how the planets move through time. I bet you guys didn't know that, and if you did, yay, because I didn't until like 4 years ago, that the planets have moved and their orbits have changed through time. Understanding how comets form and what their composition are and things like that can help us determine how the planets have moved through time through lots of numerical models and computer science that I don't know how to do, but I can contribute some. Okay, now I'm going to talk to you a little bit about the missions we've had to these comets. This is a list of all the missions. Go ahead and look at it. I'm not going to read them all because that's ridiculous, but you can see here that the first one started in 1976, and it was a NASA ESA project. So NASA, you all know, is the one here. ESA is the European Space Agency, so they're also getting to be a big deal now, so we're excited about that. You can also see that there have been quite a few missions to Comet Halley, because again, it's great. And also, you know, they had 76 years to plan it, so we're happy about that. And then what's in red is actually the missions that have failed. So usually they failed because some propulsion didn't work and they didn't get there on time, or they never launched, or things like that. And so the highlights from all these missions are these beautiful images right here. And you know, lots of science too, don't get me wrong, science is important. But really, these images are so cool. And the one in the middle, 67P, which is the Rosetta mission target, what happened is that Rosetta came, as it was further away from perihelion, followed it through perihelion to study how the gas sublimated through time and what happened when comets get close to perihelion. And then here, something that's important is you can see not only the images, you can see the gravity. It got a shape model. If you kind of have ever seen the shape model of 67P, it kind of looks like a rubber ducky. That's why they call it the duck sometimes. And also it followed some of the outgassing, so when the sublimation happens, does it happen on the surface directly or below the surface? They found these pits that couldn't be explained by craters. They're still working on that. They're trying to find morphology. They're trying to find geological activity on the comet through time. They're still looking at all of that. And it's been like 2 years since its closest approach, I think, or something like that. It's been a while. We've heard a lot about it, and it's cool. Every time you see it, you're like, oh my god, I can't believe that people actually took these images. That's not the coolest thing about comets. Okay, this is the next slide I'm going to show you. I need to prepare you guys for it. So you know how we're doing astronomy from Earth, right? We're all happy. We have spacecrafts going to comets. We're all super happy about that. But we also have an image of the comet from the surface of Mars. Okay, take that in. We're observing comets from other planets. Like, we're like aliens on other planets that are studying their stars and all of that. So Comet Sighting Springs came really, really close to Mars, within about a third of the Earth-Moon distance. So that's closer than like the 3 comets I studied last semester ever came. And so we were able, with opportunity, to look up at the sky and take an image of this comet. Okay, it's not a super cool image because you just saw the Rosetta image, but to me, that is awesome. We're doing science from foreign planets, and I think that is super cool. I'm going to say cool a whole bunch of time to convince you that comets are actually cooler than tiny, but then you'll hear the tiny talk and you'll be like, okay, maybe tiny's cool too. So, now I want to tell you a little bit about my research. Again, I love comets, hence why I do it. So first thing to understand, so that everyone knows, research is not a thing you do by yourself in your office without talking to anyone ever. You have to have many, many people collaborate with you. And that's just how science works. You have collaborator, everyone gathers data, we all share, we all pretend we like each other. Sometimes we actually do like each other. And then we do great science and publish, hopefully. So, what my project is working on, with my many collaborators, is to observe Jupiter family comets. So that's a word I haven't talked about yet. Jupiter family comets are the comets that have about a period of 6 years or so. They were captured by Jupiter, and so they orbit near the orbit of Jupiter, through the orbit of Earth, and so down to about 1 AU and a little less. And so these could be important again to determine how the solar system formed, which is why we're observing them. So our group has over 40 amateur astronomers. So people in their backyard with a kind of big telescope and a camera were like, hey, we want to observe with you. We give them filters, we give them instructions on how to observe it correctly so we can use their data, and then they're just sending us their data. And I think that's super cool. So if you have a big telescope in your backyard, you can do this too, and we can get real science. We also took data in different wavelengths of light. So for example, the Arecibo radar telescope in Puerto Rico, I went there. Yep, I did. I'm so excited. It was so fun. And we observed with the radar there. We also are observing from a lot of telescopes around Tucson. Like here we have pictured the 61-inch. It's the one where you just see the telescope. The VAC telescope on Mount Graham is next to it. Below that's the Arecibo telescope. We also use the Bach 90-inch on Kit P. We also use the MMT. There are people from the MMT apparently. Though we have not looked at that data yet, so I will not be telling you what we found. I'm sorry. But yay, the MMT is really great too. I love all the telescopes. I really do. I enjoy telescopes. So first I want to tell you about the Arecibo Planetary Radar. There are many reasons why I really want to tell you about this. First, it's awesome. Second, it does science no other telescope does. Third, NASA is thinking about closing it, so we don't want that to happen. So if somehow you get a vote in that, I don't because I'm not American, but other people who might be, tell NASA that we want to keep that telescope. It's really cool. What happens is that it's like an experiment. So most telescopes, you just take your telescope with your camera, you point it, and you hope you get light. With the planetary radar, what we do is we send light through it. So we have a giant megawatt radar that we send to the object. Then it reflects back to us onto our camera that then projects an image. This image, it has two modes, so there's some science behind how we actually get it. And so I'm going to show you one of the modes that's imaging mode. It's the cooler of the two modes, I promise. You can still get lots of data from the other one and science done. It's great, but it's not as cool looking. So this right there, that's my data. I mean, I wasn't the only one there, but I'm so proud of it. That's my baby. It's so beautiful. You probably don't think it is, but let me explain what it is. So if you're looking in the vertical direction, that is analogous to distance. So you can kind of tell how far back it goes. And this has a resolution of 7.5 meters per pixel. So what is that, about 22-ish feet, 23 feet per pixel. So you can see something that's 23 feet in size. I'm saying this, but it's actually really big. You can see that on this image. So you can tell shapes from that. And then in the other direction, it's this thing called velocity space. That's really weird, but what happens is that when you send light, it gets shifted, Doppler shifted, either blue or red, and that will be in the direction further away from the comets on the side. So from this, not only does it look cool because it moves, and you can kind of see that there's some type of feature, for example, the ridge at the top that comes towards you, so you know something's moving towards you in that direction because it's distance. And you can also kind of tell its shape and its size, and from this we can get some modeling done to get the shape. I'm not in charge of the modeling, and I don't have that result yet. We will eventually. We'll publish a paper. Everyone will be, oh my god, that's so cool, and we'll be happy. This is also one of those comets that came really close. Usually they don't come this close to Earth, so we were quite lucky to get this comet this close, plus a giant observing campaign to observe it in all the other wavelengths, and hopefully we'll be able to tell you a lot more about it. Now I'm going to tell you about the optical data that we got. It doesn't look as cool because it's not moving, but I still think it's cool. If you're looking carefully, and can I get my mouse on there? No, I can. Oh, yes, okay. So if you're looking carefully here, these are all enhanced images. So remember, the nucleus is way too small to see crap. Can we go back? Okay. There was no more trivia questions. I didn't give anything away. So you can see here the nucleus is way too small. So you're not seeing the nucleus, you're seeing the coma and the jet features that are in it. And my mother always says that she doesn't care about jets. And it's true because I talk about them too much, but they're actually really cool. So here you can see, these are different filters, which means they represent different types of gas and dust. So you can see that, or if you have a trained eye, I don't know if you do. I've looked at these way too much that I know exactly what I'm looking at, but I'll try to describe it. So those are two jets coming from the nucleus. If you look here, you only see one. Now you're thinking, why am I not pointing this part out? And that's because that is the tail of the comet, so you can know that the sun is pointing this way, right? So it's pointing this way, it's down here, pointing towards the comet, and I'm going to stop pressing buttons. But you can also see here that there's a different jet. So this kind of shows that all the comet, or all the different gases, have different jets, which we kind of already knew from Rosetta because it directly imaged different jets and was like, wait, these things are not all coming from the same place. So that means there are different areas on the comet that have different compositions. So they're not homogeneous. And then next, this one you've been, kind of seeing because I keep touching it. This one is the same filter, so it's all the CN molecule that we're looking at, but it's through time. And here you can see that there's one jet coming out. It's becoming brighter and kind of going down. And then it's still bright and lower here, and it kind of looks like there's something there. And if you look at the following time, you can see that there's the jet down here and the one up here, which means there are actually two jets on this side. And so you can kind of see it move through time, which is what we want to look at, because if you can see where it moves through time, and we have the shape model, you can try to match where those jets are on the comet itself by knowing where the sun is. This is a process that takes forever, so I don't actually know where they are yet, because remember, I don't have that shape model either. And then, because we've been talking about how comets are cool, let's talk about how cool they actually are. So, temperatures of comets varies with distance to the sun, varies with day-night cycle, varies with depth into the nucleus. And so here is just from Rosetta. And it's from once it arrives to the comet through perihelion, and these are the ranges of temperatures. So, the surface temperature of the comet, of the Rosetta comet, which is 67 P with some Russian name I can't pronounce, went from minus 135 Fahrenheit to 127 Fahrenheit. So it went from kind of cold to really, really hot. Well, not really, really hot, because we live in Tucson. It's actually not that hot. And so that's how it's submarines. And then within the nucleus, the temperature actually go much, much colder, a few kelvins above absolute zero, so minus 405 Fahrenheit to about minus 171. So they are really cool, but not always. That's the answer to the question, which one's cooler? We'll see. And that is all I have for today, so thank you very much. Any questions?
Are there any questions for Cassandra?
So many questions.